So today's lecture will be given by Dr. Thomas Jordan, who's a senior lecturer in pure mathematics. His research focuses on dimension theory and dynamical systems, and his interests also include connections between multifractal analysis, large deviations, and the thermodynamic formalism, self-similar and self-affine sets, non-conformal dynamical systems, and Fourier transform for invariant measures.
This talk will be exploring how we can describe an even distribution mathematically and also use mathematics to describe a Baker's process, eventually seeing how these ideas link with current research in dynamical systems. It's a different approach to thinking about mathematics, making abstract concepts relatable to something people encounter daily.
Okay, well, thanks a lot for that introduction, and thank you all for turning out tonight. I know you probably all have better things to do on a Thursday night than listen to more of me lecturing. Particularly, I think there's at least one person in the audience who had me at 9 o'clock this morning, so particular thanks to them. So when I got the invitation to give this talk, it came with a specified topic, which was cooking, which is a bit of a mystery to me where this came from. But fortunately, you can relate some of the mathematics I do to the process of baking. So that's what I'm going to talk about today. And so the basic problem I want to talk about is, well, here we've got some dough, and also I've got it's now stuck to it, but I've got a packet of dried fruit. And if we want to make a fruit loaf, at some point we want to mix the dried fruit into the dough so that it will be reasonably evenly distributed. We don't want it all sinking to the bottom or on the edges so it all gets burnt. We want it to be reasonably distributed throughout the dough. And so these are some questions. We can talk about how evenly do we want this fruit to be spread out throughout the dough, and what exactly we will want by being evenly distributed. Can we find a mathematical process which does this for us? And towards the end, I also want to mention that this can motivate some modern mathematics, so some current problems in mathematics research. So I am going to have some mathematics in this talk, but hopefully everything will be explained in reasonably straightforward terms. So the first question I want to think about is, what do we mean by being evenly distributed? So I'm now going to show 3 pictures of points in a square distributed in certain ways. And then at the end, I want you to vote if you wanted to think of fruit being spread out through some dough, which of these 3 pictures you would prefer. So we have our first picture. We have the second picture. And then the third one. So I'll go back through these. So this is the second, and this is the first. So if we want to have our fruit distributed throughout some bread, which of these 3 distributions would you want? Who would want to go for the first distribution? How about the second one? I think something's clearly gone wrong if you end up with the second one.
Yeah. That sounds wrong.
And the third one?
That's me.
So if I go back, so this first one, of course, everything is completely regular, but if we want this to appear coming from a mathematical process, we'll have some difficulties, because as soon as we put one ball, the first ball in the corner, then we know where everything else is going to have to be. It's immediately specified. So to actually get this sort of distribution coming from a mathematical process is going to be extremely hard unless we just put every single current in individually by hand. There's not really going to be any more efficient way of doing it. The second one, well, that's just a stupid example. So the third one is actually more what we can hope to get, because these are 400 points, and they're all chosen randomly, independently of each other. And this is the sort of thing we can see coming from a mathematical process. Now, And the other thing, going back to this one, I also think just from a cooking point of view, if you have something which looks too regular, it tends not to taste as nice as it looks. So I think that basically the random distribution is probably what we hope to get. And there isn't too much on the edges, so not too much of the fruit is going to get burnt. Okay. So, and now I want to show a quick video which is going to illustrate how you can get even distribution coming from mathematics. So here is what's called a Sinai billiard. So we started with a clump of balls and they're just being fired off towards the edges and bouncing off the sides of the surface. But as we can see, the more you apply the process, the more things get spread out. And once we've applied the dynamical system for enough time, then we get this relatively even distribution. So we started off with things all clumped together, we fired them off the edges, and we ended up with something evenly distributed. And in several types of dynamical system, this is exactly the behavior that you get. So I should say this animation is due to my colleague Carl Dettman, who actually works on a lot of computationals involved in these billiard systems. So, and also I keep using the term dynamical system. All I mean by dynamical system is a system which evolves with time. Here the time is continuous. In other situations, the time can be discrete. So this is the sort of thing we want to happen to our fruit, except we probably don't want to play billiards with the fruit, or it probably will destroy the taste. So we want to come up with a dynamical system behaving similarly to this, but we can use when baking. So if I go back to the sides, so this is what I'm saying. So certain dynamical systems we can use in this way to create these even distributions. And what we saw with the billiard, we had points starting off close together, we kept applying the dynamical system, and they ended up being spread out throughout the system. This example I showed is called Sinai Billiards, named after Russian mathematician Yakov Sinai, who did an awful lot of pioneering work in dynamical systems in the late 20th century. And then our problem, can we find dynamical systems with this property which are similar to how you knead bread? And what we have is what's called the Baker's map. And these are now the mathematical formulations. So one possible Baker's map is to start, so 0, 1 squared is just a unit square, so just a square. We've got two possible Baker's maps. The first one, we're expanding in one direction, and we're contracting by the same amount in the other direction. So we're expanding in one direction, so we're squashing and expanding the dough. And then the way these two systems differ is the first one, we expand the dough, squash it out so it's longer and thin. Then we make a cut, and we place the dough back on top of the rest of the dough. The second one, S, also on the square, is similar, except we expand, so we squash and expand the dough, but then, rather than cutting, we fold. So that's why there's a 1 minus y over 2 as opposed to the y plus 1 over 2. That's to simulate folding rather than cutting. So these are the formulas, but I want to show some pictures to maybe illustrate better. So we're starting with the unit square with some arrows to illustrate things. We then squash the dough. So we're squashing in the y direction and stretching. And here this is T, so we're cutting and stacking. So we cut it back in half, and then we place the dough on top of each other on itself. So that would be one process possibly for baking, although we're also still in 2 dimensions here, and we really want to bake in 3 dimensions. But I'll come to that in a moment. So the other alternative, S, is the sort of same first process, So we squash and stretch, but then rather than cutting the dough, we fold. So rather than having the second one goes back on top with the same direction, we fold it over on top. So I don't know. So how many of you here ever bake bread? So quite a few. So for any of you, which do you think mimics the process of kneading more, the cutting and stacking or the folding? So who would go for cutting and stacking? So nobody's going for cutting and stacking, which is good, because that's what I hoped. And for folding. Okay, so most of you. So yeah, so often, so in standard dynamical systems, often the map called the Baker's map is just given as T, and that's just simply because mathematicians are lazy. And T is slightly easier to work with than S, so people stick with use the map T. But S is certainly a more genuine model for the process of kneading bread. So, going through. So, but as I said, we really want to work in 3 dimensions. But we can do the same thing. So we start with some point. So we start with our points x, y, z on the unit cube. We then stretch and squash. So here we're going to squash in 2 directions, the x and the y direction. But we're going to squash into height. So in the z direction, we're going to squash. So you have 2x, 2y, and z over 4. And so when we apply that process, we'll change from the unit square into a cuboid, where we've got 0,2 times 0,2, and then we go down to 0.25. So if we want to go back to the square, we need to fold over to get back. So we fold once in the x direction, and then we fold again in the y direction. And so this final thing gives us our 3-dimensional Baker's map. So we've squash and stretch, fold once, fold twice, and then keep on repeating this process, and hopefully this will mean that the fruit gets very well mixed throughout the dough. So before I try and demonstrate this, so there's actually a process which I want to have at least a go at trying to describe before I try a demonstration. So this is the process called mathematical mixing, and this is what we want our dynamical systems to satisfy. So we have what we call, mathematicians write Greek letters, so we use mu to represent volume, and we have T be our 3-dimensional Baker's map. What does mixing mean? Well, it means if we have any 2 nice sets A and B, if we look at this volume of A composed with t to minus n of b, I'll show a picture which will hopefully help to illustrate what this means. Then we get the product of mu of A, or the volume of A, multiplied by the volume of B. So this is what's called mathematical mixing with volume. Nice sets simply mean sets where it makes sense to talk about their volume. And essentially what this means from a practical point of view is that if we keep applying T to a set, A, then it gets evenly spread throughout the space. And trying to draw a picture, so here's our, well, meant to represent this bowl, but I've drawn it as a square. So we've got a collection of dough, which we can think of as the set, which we can think, and inside the dough we've got a set which we think of as the set B, and then we've got our collection of dried fruit, which we can pour on top of the dough, and this we can think of as the set A. So what does this set t to the minus n of b intersected with A mean? Well, being in A means your dried fruit. So that's all. So all A is just a collection of dried fruit. What being in t to the minus n of b means is that if we apply the map t n times, then you end up in B. So this t to the minus n of b intersection A is all the dried fruit which will end up in the set B. And so what we want to know is, in the end, what proportion of what you end up with in B is dried fruit. And so we want this proportion, which is the measure of t to the minus n of b intersected with A. Actually, I should have been better. That should really be mu of B. So we should divide by the volume of B. And then that will tell us what proportion of dried fruit, when you keep on applying the map of your set B, what proportion of it will contain the dried fruit. And so what mixing is telling us is that this proportion of dried fruit is exactly what we expect from the size of the set. So the measure of the set A is just the proportion of dried fruit we start with. And so this is saying if we apply T enough times, we'll tend towards getting the proportion of dried fruit in any set that we expect. So the dried fruit is getting evenly distributed throughout the set. So, okay, I never usually get to do practicals in maths lectures. So this could go badly wrong, particularly as this has risen much more than I expected it to. Okay, so here's our dough. And I'll try and get into something roughly approximating a square to start with. And then I'm going to put some dried fruit on the top. Okay, so now we're going to try, let's go back to three-dimensional map. So we want to stretch and squash, fold once, fold twice, and if we keep on doing this, hopefully the food ends up being mixed through the dough. So it's let's see if I can get this to work. So start off by squashing and expanding. Then fold once, and stick into the paper towel, which is a bit of a... And then you fold back over. This is... So you do that. Then you expand. Then you repeat the process. So we go again, fold. I did plan to cook this, but that's not going to work now. And then fold back over, and then we start squashing again. Yes. Yeah. And fold, and then fold back over, fold here, and keep going a few more times. Fold and fold. So what I'm doing here, I think it's probably not exactly what you do when you're kneading dough, but it's reasonably mimicking this dynamical system, and it's not too dissimilar from the process you do when you're kneading dough. And it's hard to see inside, so I did bring some earlier examples. And so here's one. I don't know how well you can see, but the fruit is relatively evenly mixed throughout the bread. And what you really want to avoid is the danger is all the fruit ends up on the outside and then you burn everything. So, but just to see, we move it back onto the table. We expand the dough, fold over, and then fold, and then keep on repeating the process. And very quickly, we end up getting our mixing. Okay, so that's our three-dimensional Baker's map and the idea of mathematical mixing with the picture. And now some more mathematics. So how can we show that this dynamical system has this mixing property that we want? And the technique we use is one called coding. And what we use here is we write our points x, y, and z using a binary expansion. So you're presumably familiar with writing numbers as decimals. Well, here we're doing it the same thing, base 2 for x and y, but base 4 for z. So we write x and y in their binary expansions, and z using its quaternary expansion. And using these expansions, you're able to study the dynamical behavior of this map. And in particular, we can use these expansions to show that our system is mixing. So we write x, y, and z in these forms, and then look at how we can apply the map T to them. This is where the fact that I folded makes things more complicated, because it means that every time I apply the map, the digits keep getting swapped over, which makes things much more complicated than if we just cut it and stacked. But still, from this, we can show that our original system T has this property of being mixing. So that's how we can show this Baker's map is mixing with a bit more work. But how does this relate to other problems in dynamical systems? So we can use this to motivate processes. First of all, when I'm doing this process, so kneading, folding, folding. So when I put up the map T, our three-dimensional Baker's map, it was assuming that every time we applied our kneading, we did exactly the same thing. And obviously, if you're actually baking, however skilled a baker you are, you're not going to repeat exactly the same process twice. And so this leads to an idea in dynamical systems called stochastic stability. And here, we have a dynamical system, but each time you apply it, you add a small random, you have some random error. So you don't apply exactly the same system each time. So if a dynamical system, and you have a random error each time you apply it, which is what's much more likely to happen if you're baking. You're going to be doing something similar each time, but never exactly the same. And the question of stochastic stability is, do these slightly perturbed systems have the same property have the similar properties or as the same system, particularly as the errors get small, do the perturbed systems approach our model dynamical system? If the answer was no, then the model would be a bit of a waste of time. But fortunately, in this case, the answer will be yes, and this is often the case in dynamical systems. They have this property of stochastic stability. So you have small random perturbations. As you let the perturbations tend to zero, the behavior of the system converges to the behavior of the original system. So this is the idea of stochastic stability and the motivation for it. So we never repeat the same process. And so this stochastic model is a much more realistic model of what's going on than just our deterministic model. Then there are other things, particularly if you brought in other dynamical systems, we can ask. So you notice when I talked about mixing, I had a limit in the definition. So if you're working in a practical setting, then just knowing a limit isn't really going to tell you very much, because you've no idea how long it will take to get to that limit. If you had to apply our fold map 20,000 times in order to get to a reasonable distribution, it wouldn't be a particularly useful process to work with. So often the question asked is not just are things mixing, but how quickly do they mix? And particularly for practical applications, you want what's called exponential mixing. So and the Baker's map satisfies this. So things get mixed exponentially quickly. And that means practically you almost certainly see the mixing reasonably quickly. So rates of mixing is a very important current question in dynamical systems research. Okay, then what other models, so we've got baking here, and obviously we all want to bake, but there are other questions which you can address by modelling them with systems with similar behaviour to the baker's map. We've already seen billiards, so okay, there's a pool table over there, and if you break off at pool, you might want to know how hard you need to break off before you can expect to pot a ball. And assuming you're just hitting the balls at randomly, then potentially they would also scatter randomly. And hopefully if you hit it hard enough, you'd know that one of them would have to end up in the pocket. So again, you could ask the question about how quickly billiard systems, when you're firing several balls around a table, mix. Another maybe more useful thing where these sort of questions get used a lot is in weather forecasting. So weather forecasting is, so the weather is often modelled by similar dynamical systems to the baking model. The only difference is that if you want to model baking as working in 3 dimensions, if you want to model the weather, you probably want to work in more like 10,000 dimensions, because you've got so many different factors which affect the weather. So while you have dynamical systems with similar properties, you want to work in much higher dimensions. But you still can ask the same questions of whether you get mixing. And in terms of weather forecasting, that basically means if you are asked, what's the weather going to be like in a month's time, probably the best thing you could do is look at Bristol, the weather in Bristol in the middle of April, and look at its typical behaviour over the past 50 years. Maybe take into account some climate change, but basically, rather than looking at what the weather is now to try and predict what the weather is in the month, we're far better using the fact that we're in Bristol and it's the middle of April. Because while we can predict the weather accurately for the next few days, you get, the longer term you get, the less and less accurate it gets. And that's partly because these properties have this mixing process. So they get more and more random with time. So so some places mixing is a good thing. Some places it actually makes things hard to predict. So another simpler problem where you can think of similar ideas is card shuffling. So you've got a deck of cards. You want to know how many times do you need to shuffle them in order to, so that they'll be reasonably randomly ordered. So say you're playing poker and you don't want anybody to cheat. So you want to make sure the pack is well shuffled. And the question of how many times do you need to shuffle them, essentially, though here we're working with a finite stack of cards, again, it's this, you can ask the same question. The rate of mixing is relates to how many shuffles do you need to apply. And again, if we want things to work well, then we want some relatively quick. So again, this says it doesn't really make sense to talk about exponential, but we want some relatively quick method of mixing. So in all these different areas, you have the same idea of mixing and coming from dynamical systems. Okay. Maybe I'll go back to this billiard. So here we've got a billiard where we're firing things off edges. Now, the shape of that billiard is actually very important for this behaviour. So to get this mixing behaviour, we need this convex shape of the edges. If we just had, say, a regular square, and you were firing balls off the regular square, then you would not get this process. So the boundary here is very relevant for the fact that we get mixing. So for these mathematical billiards, is very sensitive to the behaviour of the boundary. And so we could take square billiards and get different behaviour, And we could also, so this one goes exponentially fast. You could also take a billiard where you have a shape of a stadium, and you'll have some mixed behavior. So orbits will bounce, some orbits will stay bouncing up and down almost vertically for a long time, and that will be a system where it will mix, but much slower. So here, with this diamond-shaped billiard, you get exponential mixing. With the stadium, where things can stay bouncing up and down in almost vertical directions, you get some mixing, but not as fast. And then in other shapes of billiards, you get no mixing at all. So while lots of dynamical systems have this mixing property, not all dynamical systems do have it. So it's not a case that any dynamical system will work. For instance, if I just take this dough and rotate it in my hands like this, I'm not going to do anything. The distribution of the fruit is not going to be changed at all. But if we go back to our process where we're squashing and folding, it's much easier to just do it in one direction, actually. Then we do get exactly this process which we want, which will mix quickly, and the fruit should be well distributed. Okay, so I'm slightly early, but I'll finish there.
Billiards thing, are all the balls... Sorry, we have a mic for the recording. Okay. Improve your voice to speak up. In this mathematical billiards animation, are all the balls like sent off at slightly different angles, or like is there an element of randomness when they bounce off, or what? Like, how do they initially stop all being the same?
You'd initially start them off in the same direction, but as soon as they, because of the shape of the side here, and that's why the shape of the side is important, as soon as they hit the side, then they'll start going off in different directions. And that's why they'll start to mix out. So if we just had a square, then when they hit the side, then you had two orbits going the same direction. When they hit the side, they'd stay in the same direction. But here, because we've got this convex shape, if you have two nearby points, you fire them towards the side, but then they'll bounce off at slightly different angles. And that's exactly what's causing everything to get spread out in this model. So that's why the shape of the edge is extremely important.
So they initially launched off at exactly the same angle, or
They're in slightly different positions.
oh, they're in slightly different positions initially.
So
They're clumped together, but not in the exact.
So here you could, I mean, you'd still get mixing if you started them off at the same angle. Okay. You need a microphone.
Is there a shape which mixes them the fastest?
So basically, if you see the curved sides of the edges, the more curved you make it, the faster you'll make it mix. So this is pretty fast, but if you made it to curves even more, then it would go quicker.
So you talked about weather forecasting. Is there kind of like a mathematical limit in terms of, we say, a few days ahead at the moment or a week? Is there some sort of limit that we'll reach?
I think it does very much depend on the climate. So I'm not an expert in this, but I think, you can see from I think for Bristol, an accurate weather forecast 5 days in advance is pretty rare. So for Bristol, a few days. Obviously, if somewhere with a much more stable climate, you'd be able to forecast much longer in advance.
But there has been an improvement in...
Yeah, it's significantly improved in the last 20 years.
Yeah.
But this is something where you want really powerful computers. So with this memory of computers improving massively, so is weather forecasting. But I don't know if you remember, about 5 or 6 years ago, there was a long-term forecast the Met Office used for the summer, where they predicted that we were going to have a massive heat wave in the summer. So and unfortunately their press office got hold of it, and they had these press releases saying barbecue summer. And then there were all these warnings about how hot it was going to be in the summer. And then basically for most of the summer it rained and never got above 20 degrees. But what was happening there is they run simulations, and I think about 60% of the time they got the hot summer. But what of the other times they were getting this wet summer? And then the press office got hold of it and just focused on the hot forecast. And then they got into a lot of trouble for being completely wrong, but it's just the nature of something which is unpredictable.
So I want to ask, what about the situations that using some fresh eggs?
Fresh eggs?
Yeah, or some water or milk. I don't think it wouldn't make much difference to the process. The problem, this has been sitting around my office all day, so it probably wouldn't have been a good idea to have any fresh ingredients in it. But milk or egg, okay, you might want to stir rather than fold. So if it's more moist, you might want to stir rather than fold. So you'd be actually similar to the Billiards model of this rather than this folding model, possibly if you had a stirring motion. But the thing you would want to avoid if you were stirring is just stirring round and round like this, because then you're just not moving. So you need to have some mixing going on in your stirring motion. So the motion of your stirring is going to be important.
So and attempting to use my baking knowledge I've learnt from the Great British Bake Off.
Okay.
What's the optimum number of times to apply the baker's map so that you get a mathematically satisfying equidistribution, but also so that you don't overwork your dough?
You don't need to apply it that many times to get it reasonably equidistributed. So it does depend how much fruit you put in, because the problem is if you put too much fruit, then the fruit's just going to fall off and it's going to take a while to. But I think maybe 6 or 7 times and it'll be reasonably well distributed. So you don't need to apply it that much. So I don't think the mathematics is. I think if you overwork the dough, it's your own fault. You don't need to do the mathematics.
Thanks for your lecture, Thomas. I'm on the Best of Bristol organising committee, and it was only this evening when we spoke that I found out that you were surprised that the students asked you to present on baking. Do you have any idea why they might have done that? And I thought I was quite a technical baker myself, but you've taken it to the next level. Can you tell us a little bit about what you went through preparing this talk?
I don't think I'll be eating fruit cake for a while. So in terms of what I went through preparing, I've been spending quite a bit of time practicing, trying to get the dough to right and working how much fruit I can put in for it still to. Fortunately, I hadn't. Obviously, the paper towel was a bad idea. I should maybe have brought a shopping board or something. But, in terms of why this topic was nominated, I have no idea. Maybe somebody in the audience has a better idea.
Would it affect the time in which to fully mix it if you were to split the dough up into smaller bits and mix fruit into those, and like the same amount of fruit?
If you were to, it wouldn't affect the time significantly. So you wouldn't, by splitting it up, you wouldn't save the number of times you had to fold by that much. So basically, if I split this dough into 4, the amount of times I wanted to mix the dough would be very similar for the whole thing to the smaller parts. So you'd be increasing your work quite a bit by doing that, although it might make things easier with the fruit.
Do you think following the mathematical model can improve the taste of the baking?
So I suppose I have not answered the question I had in my talk. I think the way you improve the taste of baking is by practicing it a lot and forgetting about the mathematics. I don't think mathematics in this sense, maybe other ways it can, but in this sense I don't think it's going to really help your baking. It's just a matter of practicing the process lots of times. Although there is a relation between baking and mathematics. Neither of them are good spectator sports. You can watch, if you watch lots of cooking shows, you may find that serving Gordon Ramsay raw chicken is a bad idea, but it probably won't improve your cooking that much. If you actually want to improve your cooking, you need to practice. And also mathematics is very much the same. Watching me give lots of lectures probably doesn't really help your mathematics, but actually trying to do some problems is what you really need to improve mathematics.
Did you get any pictures of your earlier attempts at the bread? And if so, could you post them to the Facebook page?
I haven't got any pictures of them, but I can maybe take some of. I've still got some examples of bread left. In particular, I've got the one which was a disaster, which maybe I can show. But that was not because it didn't mix, it was because it didn't cook properly. It got burnt on the outside and raw in the middle. There's one at the back.
You've shown you're obviously incredibly good at maths and baking. Do you have any other hidden talents that we don't know about?
Well, you've not tasted anything I've cooked. So, I mean, I like hill walking but I think I'll leave it.
Since I'm a rookie in bakery, I just want to ask, like, is it necessary to apply the constant force when you stretch and squash the dough?
I don't think it, probably you don't want to have too much variance in how you do it, but I don't think it's something to worry too much. If you just do it naturally, if you just push down and then fold over and don't worry about it too much, then it should be fine. It's not that complicated a process. You just.
I would like Thomas for giving us that very interesting lecture, who thought a maths degree could help my baking. I would like to thank everyone for coming to the lecture, and I hope you all have a nice evening. And also, don't forget to vote. The SU election is closing like half an hour, so if you have some time, if you've not voted, please vote. Thank you.